thank you for inviting me. I'm excited to be here. It sounds like I'm talking to a very informed audience. So we're going to just dive right in and talk a little bit about James Webb Space Telescope. So as many of you may know, in science and certainly astrophysics, we always have these questions that we're trying to answer, and that's why we do this exploration and these science themes. And one of those is, where do we come from? What's our place in the universe? And the other one is, are we alone? And James Webb will certainly help answer some of those questions, hopefully many of those questions. We've had other missions before, like Spitzer and certainly Hubble, more than 30 years. Unlocked a lot of secrets of the universe, and Webb is 100 times more powerful than Hubble, if you could imagine that. So just think of what it's going to bring back for us. So Webb is certainly a NASA-led mission. It's the largest science mission NASA's ever done. We have two significant international partners. We have the European Space Agency. I'll speak a little bit more about that later. And we have the Canadian Space Agency as primary partners. So the science motivation, so we know the universe is about 14 billion years old. We think that's around the time of the Big Bang. Hubble has allowed us to look back into the universe to see how things formed early on. But Hubble is limited as far as how far it can go back. And Webb goes quite a bit further, about 300 million years before, right after the Big Bang. If you could imagine that, when we're talking billions, then we're talking 300 million years as short. So it gets us pretty close. So we'll see the formation of new galaxies. We'll see as we get closer to time, we'll see exoplanets. Of course, when Webb was first conceived, we barely knew about exoplanets. And now there are many thousands of them, these planets around other stars, similar orbits as Earth around our own star, and roughly the same size or similar size. And so we think they're potentially habitable based on the Earth being habitable. So we will find exoplanets and better characterize them. And little known, Webb actually will also explore our own solar system. We'll better characterize atmospheres like on Mars, even though we have orbiters and rovers there today. They only see small pieces. So Webb will help us to actually characterize planets within our own solar system. So what is this James Webb telescope? So there are two major components, large components. One you see on the top, and that's the telescope. It's the combination of the mirrors, the primary mirror. You can see the large 18 segments, which I'll talk more about in a minute, and the secondary mirror pointing towards you. So that's one part of the telescope assembly. And on the back side of that, we have the instrument package. We call it the Integrated Science Instrument Module. That's the collection of the multiple instruments that we have there, and that are contributed by the US, ESA, and Canadian Space Agency. And all of that was developed, or mostly integrated, at the Goddard Space Flight Center in Greenbelt, Maryland, where the project is led from. And of course, below that, we have what we call the spacecraft element. On the bottom, it's the spacecraft bus itself that has all the electronics and brains of the observatory. And in the middle, that's the 5-layer tennis court size Sunshield. And so the Sunshield has two significant technologies, even though it seems like 100. One is the actual the layer itself, the shield itself. That's a new proprietary technology that took a lot of work to get us here. And then some of the systems that help deploy that were new technologies. And again, there's 5 different layers. If you think of multi-layer insulation, it's a very similar concept. And it's truly the size of a tennis court. You'll see some photos of the actual hardware in just a few minutes. So that's what makes up the entire telescope. And there are many thousands of parts beneath all of that. So again, a little bit more on the telescope and the partnership. In the middle, you'll see with multiple boxes below, That's the telescope. Up top, the optical telescope element, that's where the mirrors are put on. I mentioned instrument package below. And then the instruments, you can see just below that, near cam, MIRI, near spec, and fine guidance sensor. All of that makes up Otis. That's a telescope plus the instruments. All of that was, the top part was integrated at Goddard, as I mentioned before. And then the rest of it was integrated out at Northrop Grumman and Redondo Beach, just south of LAX. And out there is where we integrated the telescope onto the spacecraft bus and created the observatory. The other middle picture, the ground segment, middle and right, that's at the Space Telescope Science Institute. They did the ground system, and we will actually do mission operations from the Institute. We'll talk more about them in a few minutes. On the far left, another ESA contribution, and unprecedented for a mission like this for NASA to launch on a foreign vehicle and actually from a foreign land. So the Ariane launch site is in French Guiana in South America. And they also launched the Vega from there, and Soyuz has a part of the base, not run by ESA, but certainly on the same base. So we're launching from South America on an Ariane 5 rocket coming up pretty soon. So just a little bit about Hubble and Webb comparison. There are many, many comparisons. I only talk about a couple. Excuse me. One is you can see the size of the mirror itself. Hubble is 2.4 meters in size. And as you can see, Webb is 6.5 meters, which just blows your mind when you think of the size of that. And you need to put that thing inside of a rocket fairing and launch it, which we'll talk more about. I mentioned the Sunshield. Of course, Webb is operating in low Earth orbit. I'm sorry, Hubble and Webb will actually operate out at Lagrange point 2, a million miles from Earth, facing outward with the telescope. And that Sunshield will protect the telescope from the heat and light of the Earth and the sun and the moon, which will always stay on one side. So the orientation will stay the same throughout the mission life. Another thing you'll notice here is the difference in overall size of the two telescopes. And Webb is actually considerably lighter than Hubble. And again, a lot of the newer technology, the use of things like material like beryllium, that's much, much stronger than aluminum, but far, far lighter. So it gave us the ability to build a larger telescope that's lighter, so we could get this thing off the ground. So I talked about the partnership. You can see the US Webb was touched in 29 different states. And in some cases, some of the hardware, particularly the mirror itself, went to a lot of different states for different operations, in some cases more than once to the same place. And across the globe, of course, most of that's in Europe. So we had work in Canada in the partnership. So overall, 14 different countries also touched James Webb, which is quite significant. So this was out at Goddard several years ago now. It sounds funny saying that, several years. This is one of the instruments being installed into the instrument package, into what we call ISOM. That's being done at the clean room, the same clean room as Hubble. Many of you have probably seen it and very familiar with it. And I forget which instrument this is, but all of them were integrated at Goddard. So we're gonna see a lot of nice pictures here now. And this is the back plane for the mirrors. And you can see at the bottom there, one of the mirrors has been installed. It still has the cover on it. And most of these had to be installed with technicians lying flat face down on diving boards, with a lot of precision. In some cases, more than one person on different diving boards get these installed. Just an amazing accomplishment when you think about it. So this is also at Goddard. This is once all of the mirror segments, the 18 of them. Of course, they all have to work as one once they're in space and doing the actual operations. And the primary mirror that's pointing up top, you see those arms coming down. That mirror actually deploys towards you and creates the position for the secondary mirror. So this was the first big deployment of the telescope at Goddard prior to all of the testing that took place. The mechanical testing took place at Goddard and just a couple of doors over from the high bay. That's where we did the acoustics testing and the vibration testing of the telescope. And of course, we don't have a chamber large enough at Goddard, not many in the country, large enough to do, and with the right temperature characteristics to test this thermally, which we have to do before so we can operate in space appropriately. So what do? This is a Apollo Chamber A that was used for Apollo down at JSC at the Johnson Space Center in Houston. So we actually had to do the thermal vacuum testing of the telescope down there. Of course, it was retrofitted just for this purpose. It can get to the right temperatures at different locations in there to do the appropriate test. And coincidentally, the telescope arrived there and the testing started right as Hurricane Harvey was coming in. So a lot of people some had stayed at hotels, some slept on little cots right outside the chamber and just kind of rode out the storm. And another interesting fact there is many of the people working on this down at JSC actually went out into the community to help out, get people out of harm's way, which was greatly appreciated. And this is inside the chamber, down at Chamber A in Johnson. You can see a lot of things suspending the observatory to offload some of the gravity effects. So the temperatures will impact the observatory exactly the way we want to. And it got very cold in there. We got it cranked it way down, pretty close to absolute zero, not quite, but pretty close, because we know we'll see that in space. So this is the full telescope, the mirror, primary mirror and the secondary mirror. You don't see 18 segments on each side. There are 3 mirror segments that are folded back. That's how it will actually fold back so we can fit it inside the rocket fairing for launch. So you're going to see in just a second the secondary mirror deployment test. And what you may not be able to see, there are some strings coming down from the ceiling, holding on to the mirror itself. You probably can see one right here, to offload the gravity effects, because of course in space it's going to deploy with no gravity. So we're trying to create that same test as you fly environment here on the Earth. So you can see this deployment occurring. Much slower than what you see here. And we did that a couple of times. That was a really big deal to make that happen. You can see some of the strings or wires holding it there. Pretty fascinating. Keep going. So here you would see the telescope off to the side. You see the spacecraft bus. The Sunshield here is still folded. It's not deployed. So this was after the telescope came from the Johnson Space Center in Houston out to Northrop Grumman in Redondo Beach, California, and we had to integrate the two. So you're going to see this in just a minute. And as you can see there, the telescope was integrated to the spacecraft bus. We deployed the Sunshield. So that was the first major activity integrating everything into one package. And believe it or not, that was August, September, October of 2019. COVID makes you lose a year or two in your thinking, but we got that done. So after we got everything integrated, we deployed everything, we put it in the stowed environment. You can see this, the Sunshield folded up and up with the two field goal looking things on the end. And of course, you can see the telescope folded up as well. And this is what we call the flight configuration. And we had put it in this configuration so we could do our final environmental testing, which is acoustics and vibration. And this was done out of Northrop Grumman. And the two halves, the spacecraft element and the telescope, went through thermal vacuum separately. So there's no way we could have deployed both of those and tested them in a chamber. Just no capability available. And this was the full deployment of the Sunshield. And certainly the telescope still has the wings folded back on either side, the three on each side. It takes quite a while to get the Sunshield deployed. It's a long process. Each layer is deployed separately, as you saw in the video. We have to deploy five layers of that. And of course, you can see all the little cherry pickers out there. We have a lot of diving boards in the high bay. Access is a real tough thing. It's a big deal. But again, we got it done. And you can see the size. Look at the people there, just the size of the telescope overall. It's magnificent. And this is the mirror fully deployed. You can see the wings on both sides fully deployed. That's what it would look like when it's in space. Except for the secondary mirror will deploy out towards you, as you saw in the earlier video. And this is the Sunshield folded up again. You see on both sides what we call the unitized pallet system, UPSs. So we fold it up, we put a cover on top. On the left side one, you can see the cover is on a slightly different color, and we haven't put it on the back side just yet. And here, this is a fully stowed after the testing, more integration work, fully stowed observatory. Again, you can see the Sunshield folded up with the UPSs. You can see the mirrors folded up in the flight configuration. And of course, you see all of the mechanical ground support equipment there all over the place. So high bay was very crowded. And we had to keep this extremely clean during all of this time. And there were many protocols and cleaning activities to maintain a certain level of cleanliness. And this is also fully stowed. This was just several weeks ago. You can see on the left of it and on the right of it, the silver looking thing, that's the shipping container. On the right is where we actually laid it in, and on the left is the cover for the shipping container. And I don't think I have the video for that. I don't. So basically we transfer this over to what we call a high capacitor rollover fixture. We connect it there and we can turn it to horizontal, and we can move it over and put it in with a crane, of course, and put it inside the shipping container. So we talked a little bit about the ground segment, mission operations, and this is at the Institute. Here you can see them doing launch, what we call LREs, launch readiness exercises. Long rehearsals, 1 week long, 2 weeks long. We're just finishing up one this week for 2 weeks. So the team is ready, the ground system is ready, they're well trained. We've gone through a lot of, we put in a lot of anomalies, they have to recover from it. So a lot of contingency work to get the team sharp and ready to go. And the Institute is actually in Baltimore, for the ones who don't know. So we, a couple of weeks ago, we shipped this from Northrop Grumman, from California. And I mentioned we're launching out of French Guiana down in South America, just south of Guyana and Suriname, and just north of Brazil on the Atlantic coast side. And the ship in the middle is a ship that's used to ship hardware on a regular basis from Europe for ESA and Arianespace and others down to the launch site for launch. And you can see on the right a pictorial of the spacecraft inside the launch vehicle fairing. That's how it will actually look. And here, this was the ship. We shipped from Seal Beach, just south of LA, just south and north of Grumman, on the same ship. And this is the ship arriving in South America, approaching the Kourou River and coming up to the port in Kourou. And this is the CSG, and don't hold me to what that stands for, but it's the center down there in French Guiana for all the launches. And you can see the mock-up of an Ariane 5 right there in front of you. And down on the road, that's the large white shipping container. So the truck is pulling it to the base from the port. And the truck is pulling it off of out of the belly of the ship, the garage, we call it, and heading over to the base. And the shipping container coming in to the high bay down there. And you can see the top coming off on the bottom right. We took the observatory out, put it on that H-cross, the high capacity rollover fixture, and getting it ready in the high bay for an inspection, make sure everything worked out during the voyage, which it did. We will do our final comprehensive system test. I think it started a couple of days ago. That'll last about a week and a half. That'll be the last major functional tests of the observatory. And there are 3 buildings connected there. First one is for spacecraft processing. We'll be there for a few weeks. At the appropriate time, we'll move over and get it fueled, and another part of the building, it's a separate building, but all connected under one big roof. And then the next one, we've made it to the rocket stage, encapsulated into the fairing, and then we'll move it to another building where the rocket is already stacked, and we'll put it on top of the rocket and roll it out to the pad for launch. So this is the launch site. That's an image of a Ariane 5 launching just a few years ago. Pretty nice image. I'm looking forward to that again. And on the 18th of December, we'll be launching out of French Guiana. Again, we're going to Lagrange point 2, pretty stable orbit, about 1 million miles from the Earth. And just looking at the way Hubble sees the universe and the way Webb will see it, going from infrared to mixing optical and infrared together, it gets much clearer over time. You can actually see through the gook and fog and everything in space to see a much clearer picture. So after we launch, we have 6 months of commissioning. At the Institute, we have the first phase of launch. We have about a month of course, right after launch, you get the antenna signal and the solar array deployed, so we have power. And then about 3 weeks to a month after that, we will actually be doing all those deployments we talked about, the telescope, the Sunshield. There are other small Sunshields on the edges, and other types of deployables we'll be doing over that period of time. There are a few burns in there to make sure we head in the right direction to get the right orbit. Then we have a period where we start cooling down. The spacecraft, for space purposes, is still very, very warm. So there will be a long period of cool down. During that period, we'll start adjusting the mirrors, make sure that they're working just right, that all 18 of them are working together. We'll start turning on instruments and making sure that they're working. And of course, there's a long cool down period. That's just physics. There's nothing we can do about it. So the first 4 months, it's just the deployments, cool down, turning on instruments, and getting ready for an operational mode. And then the last 2 months, we'll start taking images with the instruments, again, doing a lot more corroboration between the instruments and telescopes and each other. And hopefully right at 6 months, we'll be releasing things along the way, but right at 6 months, that's when we look forward to getting what we call that first big image, first light, to see what the universe looks like. And at that point, we'll go into full operations.